In this video, we look at what's called the Cartesian form, a different way of representing vectors. So we now know that some quantities need more than just numerical size representation, and vectors are one way to represent quantities that need a size and a direction. The geometrical form that we introduced first is often difficult to work with, and sometimes relies on us being able to draw pictures. The Cartesian form, or rectangular form, is often much better to work with. Here we're going to look at how to work with this particular form. The first thing we need to do is introduce a coordinate system with coordinate axes, like the ones that you're used to seeing in the familiar xy plane. What we're going to do is define I to be a vector of length 1, or a unit vector, in the positive x direction. You can see that in the red line down the bottom here. Similarly, we define j to be a vector of length 1, or the j unit vector, in the positive y direction. You can see that here in the green arrow. We call the I and j vectors of this type the standard basis vectors for two-dimensional space. We can express any point we like and the vector that represents that point in 2D space as a vector in terms of I and j. So an example shown on the right has a point x equals 2, y equals 1, and the vector which moves from the origin to that point, and we can see that we can represent that vector, the blue one, in terms of two lots of i's and one lot of j, or 2i plus j. We can think of it that way because of the triangle law we already know from our geometrical form. We can do the same thing for any point we like in two-dimensional space, representing that point using a vector just like this r vector. We can do the same thing in three-dimensional space by defining a k unit vector in the positive z direction. In fact, we can do the same thing in any dimension we like, 4 dimensions, 5 dimensions, and so on. Sooner or later though, we run out of letters to represent the basis vectors, so sometimes we'll represent our Cartesian form vectors in this form, which is kind of like a column vector, or a column matrix if you like, where each of those numbers, x, y, and z, would be the coefficients of the unit vectors that we talked about earlier, ij and k in 3 dimensions. So here, this r vector would be the same as x in the I direction, plus y in the j direction, plus z in the k direction. Now you see that I've written my vectors there with little hats on top of them. That's a symbol that we use to indicate that a vector has unit length. So xi plus yj plus zk can also be written in the column matrix form. One of the big benefits of writing vectors in this Cartesian or rectangular form is that the rules for summing, subtracting, and scalar multiplying vectors become a lot easier. The sum of two vectors written in this ijk form is simply an ijk vector with the individual coefficients added together. So the I coefficient of x added to the I coefficient of y, and so on down the line. Subtraction is done similarly, with subtractions in between instead of plus. The scalar multiple of a vector is just the scalar multiple of each of the individual components. So with x equal to x1i plus x2j plus x3k, we simply multiply x1, x2, and x3 by k. The magnitude of x is given by Pythagoras' theorem as usual, and if we move up in dimensions, it simply has an extension that follows pretty logically from what you'd expect. We simply add on the square of the next component. Okay, so let's try out these new rules with an example. Here we're given three vectors, a, b, and c in 3 dimensions, written in the rectangular form with I, j, and k unit vectors. We're asked to find the sum of a and c, 2c minus 3b, and finally the magnitude of a. Have a go at this yourself, but pausing the video now and trying to work these problems out using the rules that we've just introduced on this previous slide. The first part of the example asks us to add a and c. The rule on the previous slide tells us that when we add vectors, we simply add the coefficients from each component. So in this case, we'll have the I components, 1 plus 8 in the I direction, plus the j components, negative 2 and 7 in the j direction, and finally the k components, 2 and 1. Adding all of these up we end up with the resultant of 9i plus 5j plus 3k for the sum of the a and the c vector. In the next example, we're asked to first multiply c by the scalar 2, and then b by the scalar 3, and then subtract the two results. Multiplying each of the components of the c vector by 2, we obtain 16i plus 14j plus 2k. Multiplying b by 3, we get 6i plus 9j minus 3k. Now all we need to do is subtract these two. And again, we do this component by component. So we end up with 16 minus 6, or 10i, 14 minus 9, or 5j, and finally 2 minus 3, or plus 5k, as our result for 2c minus 3b. Finally, we need to find the magnitude of the a vector. That's just an extension of Pythagoras' theorem to 3 dimensions. So we need the square root of the sum of the squares of each coefficient. The coefficients are 1, minus 2, and 2. So we have 1 squared plus minus 2 squared plus 2 squared. Once we add those up, we take the square root. So 1 squared is 1, minus 2 squared is 4, and 2 squared is 4 again. So we have the square root of 9, which is of course 3. And so we have that the magnitude, or the length of the a vector, is 3. We've already been talking about the idea of a position vector. That is, a vector which represents any point in space. We've been mainly looking at 2D and 3D space. So generally we can say that for a point in space with coordinates, say x, y, z, we need to move x, I basis vectors along, then y, j unit vectors, and finally z, k unit vectors. All of this away from the origin. So to represent a point x, y, z, we use the vector r equal to xi plus yj plus zk. This representation, along with our geometrical rule for the triangle law of addition of vectors, allows us to represent what's called a displacement vector, or the vector that represents the displacement between two points. We might want to know the displacement between, say, P1 and P2, which we can represent as the d vector, if we know the position vectors for P1 and P2. Let's call them R1 and R2. The triangle law says that the vector R1 plus the vector D will be equal to the vector R2. If we rearrange this, subtracting R1 from both sides in the usual way, we end up with R2 minus R1. Gives us the displacement vector D. So that's how we can represent that displacement from P1 to P2. And of course, going backwards, P2 to P1 would simply be the negative of that vector. Let's see this in an example. Say we know 2 points, P1 and P2, and their coordinates, and we want to find the displacement between them, the P1 to P2 vector, which looks something like this. We can calculate that displacement vector by subtracting the position vectors to P1 and P2. Using the rule from the previous page, the vector from P1 to P2 will be the R2 vector minus R1 vector, or in other words, the vector from O, the origin, to P2, take away the vector from the origin to P1. Now remember that these position vectors are simply given by the vector made out of the coordinates of the point. So O to P2 will be 2i minus k, and then we need to take away the position vector of P1, which is I plus 2j plus 3k. Remember to pop that in brackets so that we take away each component. Then we can take away 2 minus 1 leaves us with 1 in the I direction. No j's, take away 2 j's is minus 2 j's. And finally minus a k, take away another 3, leaves us with minus 4k. As our vector, here the red vector joining P1 to P2. In other words, the displacement vector from P1 to P2. To finish off the example, we're asked for the distance between P1 and P2. The distance is just the magnitude of the displacement, or the length of the displacement vector. So we need to find the magnitude of the vector P1 to P2. And this will just be given by the square root of the sum of the squares of the coefficients. 1 squared, minus 2 squared, and minus 4 squared. That's the square root of 21, which we can leave in exact form as the distance between those 2 points. When we first introduced the basis vectors I, j and k in the coordinate directions, I referred to them as unit vectors, vectors of length 1. We can have vectors of length 1 in any direction we like, and to find such a vector, we simply divide a vector by its own magnitude. In fact, that's one way that we can represent the direction of the vector. So here we see the r hat vector is equal to the r vector divided by its own magnitude, and we call this the unit vector in the direction of r. In the previous example, we found the displacement vector and the distance between 2 points P1 and P2. Here we're asked to find the unit vector that represents the direction of that displacement between the 2 points. Taking from the previous example P1 to P2 vector and the magnitude of that vector, we can then say that the vector in the direction of the displacement, let's call it r hat, is going to be equal to the P1, P2 vector divided by its own magnitude. So we have 1 on the square root of 21 in the I direction, take 2 on the square root of 21 in the j direction, and finally take 4 on the square root of 21 in the k direction. This final vector has a length of 1 and points in the direction from P1 to P2. So where to now? As usual, if you're looking in other texts, check out any section that introduces vectors in rectangular or Cartesian form, and also the ideas of magnitude and direction associated with that form. Attempt the exercises from the worksheets, and then have a bit of a think about this. How might you represent a point in space if that point moved over time? That is a position vector that varies with time.